Hey, welcome back. In this video we are going to learn carbonyl alpha substitution reactions. That is the third class of the reactions that we have seen up until now. So we saw nucleophilic addition, we saw nucleophile acyl substitution, now we are at the carbonyl alpha substitution reactions. The last one will be the condensation reactions that are coming after those videos about the alpha substitution. Let's dive now to the reactions and the mechanism of the alpha substitution reactions. Now, in the case of alpha, why is called alpha? Because this carbon here that is connected straight with the carbonyl group is called alpha. If we move another carbon away, it's called beta, and so on. It can be converted to an enol or enolate, depends on the condition. Basic condition, acid condition, and it can react with an electrophile to yield an alpha-substituted compound, right? Because this position here, again, is called alpha position. In terms of mechanism, alpha substitution mechanism, no need to memorize it because we are not in the advanced organic chemistry here, but just to give a general idea, in acidic condition, ketone tautomer, for example, the H3O+ is going to do protonation of the oxygen, and after that we have a resonance structure here. This proton that was taken from the oxygen here is going to remain after that as a base. It's going to abstract this hydrogen here, and we are going at this position here that is called an enol tautomer. So ketone tautomer, enol tautomer. Keep in mind, tautomer means that you have rearrangement of the atoms, right? And this serves now as a nucleophile that attacks an electrophile, and the electrophile is connected to the alpha position. And after that, one hydrogen is removed here and you stabilize this carbonyl group here to form an alpha substitution reaction. We do not, in basic condition, we are not capable of doing protonation, so we are going to remove straight the hydrogen to the alpha position, and after that you are going to form an enolate. This enolate after that is going to form a resonance structure with this compound here, and this is going to remove one hydrogen from this molecule of water, and after that you are going to have a rearrangement to form an enol again. Let's put those mechanisms in action now. Alpha-Halogenation of aldehydes and ketones. This kind of reaction works only with aldehydes and ketones. You can react with chlorine, bromine, or iodine in acetic acid, and you can yield an alpha-substituted product. In this case, going to be substituted to the more substituted position. And if you treat with pyridine, you're going to remove this chlorine and to form a double bond here at the alpha-beta position, and this substituent is going to remain in its place. Okay, let's move now to alpha-Bromination of carboxylic acid. This requires a specific mechanism. It's called Held-Volhard-Roselinsky reaction. And it requires phosphorus 3 bromide to happen, but at the end the same product is going to be formed, and again the same thing is going to happen, alpha-substituted halogenation. So, right, this is the alpha position related to this carbon here. Let's move further. Enolate formation, how we are going to form enolates. Lithium disopropyl amide is a typical one that is a strong base used to convert the carbonyl compounds to enolates. How it is formed, disopropyl amine reacted with butyl lithium in THF solvent, tetrahydrofuran, and you're going to form this aldehyde in a short name. And when you treat a ketone, for example, cyclohexanol in this case with aldehyde, you're going to form an enolate product. Acidity of hydrogen atoms in the middle of the two carbonyl groups increase. What this means? This means that the hydrogen atoms in the middle of those two carbonyl groups are more acidic. How are they more acidic? If we treat with a base, we are going to remove, for example, this hydrogen, and this lone pair here has the possibility to move in both sides by creating resonance structures. More resonance structure for a compound, more stable. In this case is an anion, so this is translated to a higher acidity of those two hydrogens that have the possibility to dissociate easier. Let's move further. Reactivity of enolate ions. They are more useful than enols due to the higher stability, easy preparation as a pure compound. we have these two possible structures. This structure here, that the reaction happened to the oxygen and with an electrophile and forms a vinylic alkoxide, and it forms enol derivatives. We are not going to focus here. We are going to focus to the reaction that happens to the alpha carbon. Let's take a look at this compound here. The reaction happened at the alpha position, that is in our interest, and is going to form an alpha substituted carbonyl compound. Our focus will be on this type of reaction. Haloform reactions. When you treat a methyl ketone with bromine in basic conditions, what you're going to form, you're going to have bromination of these 3 hydrogens here to form the haloform, this compound here. How it happens? The bromine attaches first here, and after that this hydroxy attacks the carbon here, because this becomes more electrophilic, and you have the formation of the alkoxide intermediate, and here you have a nucleophile acid reaction mechanism, because this group goes away and this turns here, and what you're going to have at the end looks like you have the formation of the carboxylic acid with this anion, but the final product is that this hydrogen is going to be catched by this carbon here to form 3-bromomethane or haloform product, plus this remaining salt. Okay? Let's illustrate again to memorize this one. As a general, is going to be an oxygen here plus CH3, right? This is the final product of haloform formation. Alkylation of enolate ions, the most important one. If you have a carbonyl compound that contains hydrogen at the alpha position, you can treat that with sodium hydroxide or sodium ethoxide, and you can convert that to enolate. And this enolate after that is going to react with an alkyl halide through SN2 mechanism to yield the alpha-substituted compound. The rules for this second step here are the same as with SN2 reactions. You can check this video here if you want to learn more about SN2 reactions. The conditions are the same as with SN2. X should be an tosylate, reactivity increase on this side, iodine, bromine, and chlorine, and the R can be allylic, benzylic, methyl, or primary halide. One of the oldest syntheses was Malonic ester synthesis. This does the addition of the 2 carbons to the alkyl halide. So in simple words, convert an alkyl halide to a carboxylic acid with 2 carbons in addition. So it extends the alkyl chain by 2 carbon. Simplification here, ET is ethyl, right? Malonic ester synthesis, Malonic is a common name, so the UPAC name is diethyl, this compound here, diethyl propandioate or Malonic ester. Both ways works fine. You can treat this compound with sodium ethoxide in ethanol. ET means the ethyl group with an OH forms an ethanol, you understand this. As I was mentioning above, those hydrogens that are between 2 carbonyl groups, they are more acidic, and we use this property to form enolate. You can remove both those hydrogens and displace them with alkyl halides to form more complex structures. So in this case, for example, if you remove only this hydrogen at the first stage, you can react with methyl halide in this case. You're going to form this compound here. Now, in order to remove the ester groups, you're going to do decarboxylation in hot conditions with normally is carried out with hydrochloric acid. If you want to substitute even this hydrogen, you do not carry out this step first. You do again enolation to remove this hydrogen here, and after that you can add another compound, depends on the synthesis that the professor is giving you in the exam. For example, benzyl bromide here, and you can add this here, and after that you can do decarboxylation with hydrochloric acid in hot conditions, and this is the final product that you end up. Right, as a conclusion for this final product, those 2 carbons come from the Malonic ester, right? From this compound here. This contributes with 2 carbons. Okay, with Malonic esters you can form cyclic alkanes also. We can start from Malonic ester, treat with sodium hydroxide in ethanol. You can form enolate, and after that you can treat this enolate with an dihalloalkane, so two halogens in the terminal sides of the alkane. And first you're going to connect on one side, and again you're going to, in a second stage, to remove the next hydrogen and treat that with sodium hydroxide and ethanol. You remove the second hydrogen, and this is going to react now on the other side of the alkyl chain to remove this other bromine, and at the end what you're going to form 1, 2, 3, 4, 5, 6 chain member ring. So you have a 6 members ring here, and after that what you're going to do H3O+ with heat to form the carboxylic acid. Here looks like that you have added only one carbon, but instead you have added two, because also this carbon is this carbon here, right? Be careful here, right? Because we added 1, 2, 3, 4, 5, not 6 carbons. This carbon is contributed by the Malonic ester. And of course you have CO2 and 2 ethanol molecules from the esters. Example, how you're going to find the Rx and Malonic ester. So Malonic ester should be this part here, that comes from Malonic ester. This part here comes from the alkyl halide, right? For example, it's going to be this one. And this one is going to be the Malonic ester. Okay, another type of synthesis is acetoacetic ester synthesis. Here you add 3 carbons and you convert the alkyl halide to methyl ketone, right? So Rx to methyl ketone. So the same strategy is also here. You treat with the sodium hydroxide and ethanol to remove the hydrogen that is acidic, because again it's between 2 carbonyl groups, and you can add, for example, this. The rules are the same for the second stage because it's again according to SN2 mechanism. You can add this compound here, and after that you can go straight to do decarboxylation and to yield the methyl ketone, or you can add another group or substituent to the alpha position by treating again with sodium hydroxide in ethanol, and after that you can add, for example, this benzylic group. And you can form this big compound that, treated with H3O+ in heat, in acid conditions, you're going to form this final product. So you can build complicated structures on this way. It works fine with all beta-keto esters. Keep in mind beta-keto esters because the ester has the highest priority ester group. That's why beta is to this carbon here. So alpha-beta related with this carbonyl group that forms the ester. You can treat with sodium hydroxide again, and you, as a second stage, you can add this primary halide to yield this compound, and H3O+ plus E to yield this compound, right? Even with acetoacetic esters, you can form cycles. You have to be careful because this carbon here belongs to acetoacetic ester, right? Because you need to add 3 carbons, 1, 2, 3. For example, what are the components of this one? Acetoacetic ester and these 1, 2, 3, 4, 5 carbons that comes from dehalogenated in terminal sides of the alkyl halide, right? You can do also direct alkylation of ketones, esters and nitriles with a stronger base, such as lithium diisopropyl amide. You can try it with here at this cycloketone in THF. Be careful, you have here the formation of 2 products. Again, goes according to the SN2 mechanism with primary halides. With esters, again, you can do halogenation at the alpha position, and with nitriles, you can do alpha substitution. Let's go to some examples now. Multi-step synthesis. So the first stage to form the enolate, that was sodium hydroxide, and the second stage add this CH3 iodine, for example, right? Now from here to go here, it is done decarboxylation. So how we did that? H3O+ in heated condition, hot conditions, right? And from here to here we have done a direct alkylation. So we learned just above LDA in THF as a first stage, and the second stage was the CH3I, right? We have also other products formed, but this is the major one. Let's move further to the second example. From this compound to this compound. Do you remember what was the intermediate or the reagent to go straight here? It was a specific one, I'm going to link that video right here, is a Wittig reaction. So what we did, straight to form double bonds. So was 3-phenyl phosphorus CH2 minus, right? And you can go straight here, and at the end the Wittig is going to be transformed to the oxygen. So this oxygen is replaced by the CH2 and form a double bond, right? Let's move to the point B. This alkene, to convert it to alkyl halide, first you have two steps here. The first step is that you have to convert this with non-Markovnikov product BH3 DHF H2O2 OH minus to convert that to a primary alcohol CH2OH, and after that from here to go here, you know, phosphorus 3-bromide in ether, right? Let's move further. From here to here, you understand that is done an alkylation to the alpha position. So how we did that? First LDE in THF, and second is this phosphorus CH2Br, right? And now what we are going to do from here to here. Now we have a carboxylic acid. So now from an alkyl halide to carboxylic acid, it remembers us Malonic ester synthesis. What was the Malonic ester? ETO2 CH2, again CO2 ET at ethyl. So this one was treated with sodium hydroxide in ethanol, and you had the formation of this enolate. Right, and this one is going to react with this compound here, right? And this is going to attack this one here, and this one is going to go away. And as a final product, because you're going to have the formation of this compound, to go to this one, you need H3O plus in hot condition, heat, plus this what remains, CO2 plus 2 molecules of ethanol, right? Malonic ester synthesis. Let's move to the last example. Here you understand that you have two steps. First, you are going to do bromination in acetic acid at alpha position, right? And after that, what we did with pyridine, you are going to have the elimination of bromine to form this double bond in alpha and beta position, right? Okay, that's it for alpha substitution reactions. Thank you so much for watching, and look forward to see you in the next videos that are going to be with carbonyl condensation reactions, specifically with aldol condensation first. Up until there, peace.